Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 43, part A. We are now moving into section 5.2, which is bivariate transformations or bivariate inverse transformations. Our book calls it functions of two random variables. So in the last section, we discussed univariate transforms or univariate inverse transforms. We discussed both the discrete transformations, which have to be done using logic, and then we discussed continuous transformations, and there were three methods or three ways to do something. And I see that I just have a typo. That's supposed to be one-to-one. So we have the CDF method. We have the one-to-one univariate transformation theorem, and then we have the K-to-1 univariate transformation theorem. We also proved the CDF theorem, which says that if the CDF is strictly increasing, then it is distributed, so f of x has a uniform distribution between 0 and 1, which is a very handy thing when you start doing research and programming. Okay. Now, in this section, we are going to discuss bivariate transformations. We're going to start with the continuous case and discuss these bivariate or inverse transformation theorems for one-to-one functions of x and x and y, and k-to-1 functions of x and y. And then we will, I don't think we have this, we don't need to do that again. And then we will discuss discrete transformations or transformations on discrete random variables. So, I'm going to try to go slow, and I hope that you will take time to try to absorb this information because I understand that it's very intimidating at first. Okay, so we're going to say that the bivariate distribution of x and y is f of x, y. And then we're going to say that u is g1 of x and y, and v is going to be g2 of x and y. And we want to find the joint distribution of u and v. So u is a transformation of x and y, and g, or a function of x and y, and v is a function of x and y. Okay? Then the transformation theorem, and again, this is only applicable for continuous random variables. Assume that the transformation from xy to uv is 1-to-1. So this has to be true. So this is the 1-to-1 transformation theorem. It only works when it's a 1-to-1 relationship. We'll go over the k-to-1 relationship later. So just suppose that x is equal to h1 of u and v. So what is this? So what we just did was we said that u is equal to g1 of x and y. And then we're going to say that x is equal to h1 of uv. So this is an inverse function. So this is going to have to be some type of g1 inverse on u and v. Okay? All right. So x, we're going to call it, the inverse for x is going to be h1 of u and v, and y is h2 of u and v. And these are the inverse transformations from u and v back to y. The joint PDF of u and v is given by, and so now we're going to have a more complicated but similar transformation theorem as we did in the univariate case. So now we have f of h1, h2. So I could write this with a lot more symbols. This is going to be f of h1 uv, comma, h2 uv. And remember that h1, this is x, and this is y. Okay? So for where we had x plugged in, we had f of x, y. That's the joint PDF of x and y. We're going to replace x with the inverse transformation from u and v, and we're going to replace y with the inverse transformation from u and v. And so by doing this, we're going to change from x to u and v. And then we take the absolute value of the Jacobian. Now, students get this mixed up. This is an absolute value. Okay, so we are going to take the positive. So this is an absolute value. But don't get that mixed up with the determinant. This is not an absolute value. This is a determinant. Not an absolute value. So once we take the determinant, we still have to take the absolute value. And so what we have here is we have the partial derivative of h1 with respect to u, and then we have the partial derivative of h1 with respect to v. And so you can think of this as h1 is on the top and h2 is on the bottom. Now, you could do v, you could reverse these, and it will be fine. You could do them backwards. You could do, this is u, and this is v. So, okay, so this has to be the same. So this is u, so these are u, and these are v, and they have to be that way, all right? So, sorry for that typo. I just noticed it. So I can switch I can switch the whole column, and I'll get the same answer. So if you do that, it's okay. You'll get partial h1 partial v partial h1 partial u, but then you have to do the same thing on the bottom. This has to be v, and this has to be u, okay? So it really doesn't matter which one is u, which one is v, is what I'm saying in this case. Just keep them straight, whichever you have defined. Okay, so this is going to be, how we determine this, this is the partial h1 partial u times, so we do this, these diagonals times each other minus these other diagonals. So this is going to be partial h1 partial u partial h2 partial v minus partial h1 partial v times partial h2 partial u. So that's how you do a determinant of a 2 by 2. So for bivariate, this is easy, okay? When we get to multivariate, then you have to learn how to do determinants of 3 by 3, 4 by 4 matrices, and it's a lot more complex. Okay, so again, this is the absolute value of j. So j absolute value is the absolute value of it. So this does not have to be positive. Okay, it does not have to be positive. In fact, it can be negative, it can be positive, it can be 0. Okay, so let's do an example. Let x and y be independent normal 0, 1. The way I can also say that x and y are, I won't do it like this. I don't need the parentheses. I'm just going to say x and y are IID normal 0, 1, and IID equals independent and identically distributed. So they are identical except that one is in terms of x, the other is in terms of y. But they are independent, and that is the important part here. So they're independent normal distributions and normal random variables, sorry. And so the joint PDF of x and y is given by f of xy equals f of x, f of y multiplied. And so that is what we've done here. I know this looks kind of strange, but those are 2 parentheses. Is what that's supposed to be, not a division or anything. And so they're standard normals. So here is the PDF, 1 over square root of 2 pi, e to the negative x squared over 2, 1 over square root of 2 pi, e to the negative y squared over 2. And don't forget the range of x and y. Okay? So we have a is equal to negative infinity to positive infinity for x, and negative infinity to positive infinity for y. They're both normal distributions. So you really need to know the range of these distributions, right? So that's why I've been very particular about making you write the complete PDF with the range of x and y, because you'll need that to identify some of these distributions. So they have, so these are two normal distributions that are independent. I'm going to let u be the sum of x and y, and v be the difference, x minus y. So now I need the inverse transformation. So the first one is I want to solve h1 of u v equals x. And so that's going to be u minus y. Okay? And then I'm going to do the same thing for y, and I'm going to use the other variable, or the other relationship. So this is going to be h2 of u v. Now I'm not finished, of course. So y is equal to this. I'm going to substitute this in for y here. And so then I get u minus x minus v, which is u minus x plus v. And so that is equal to x. And so if I take and add x to both sides, then I get 2x is equal to u plus v. And now I solve for x, and x is equal to u plus v over 2. And again, this is my h sub 1 u v. I can do the same thing now for y. I have x minus v. I'm going to substitute in x here. So this is going to substitute in for x. And so I end up with, let's see, what did I do here? Okay, so I didn't substitute this in. I could have for x. What I did was I substitute in that x was equal to, so I have y, x minus, and then I have u minus y. So I used x equals, u minus y. So I substitute that in for x, and I ended up with u minus y minus v, and again I get u minus v minus y. I add y to both sides. I get 2y is u minus v. So there's more than one way I could have used this, but I didn't, probably because it's a little more algebra to use that one. And so introducing a fraction. And so then I solve this for y, and I end up that the y is equal to u minus v over 2. X is equal to u plus v over 2. So this is h sub 2. This is h sub 1. Now I need to calculate my Jacobian. Remember that the Jacobian is equal to the partial h1 partial u, partial h2 over partial v, partial that's h1 at the top, always. So partial h1 partial v. This is partial h2 partial u, partial h2 partial v. Okay. So when I take x, the derivative of x with respect to u, remember that x equals u over 2 plus v over 2. If I take the derivative with respect to u, then this is 0. So I end up with 1/2. If I take the derivative of this with respect to v, then this is 0, and this becomes 1/2. And the same thing here, when I take the derivative of this with respect to u, you can rewrite this as u over 2 minus v over 2. And when I take the derivative with respect to u, I get 1/2. But when I take the derivative with respect to v, I get negative 1/2. And that's very important. If you mess up these signs, you're going to get the wrong answer, and it'll really mess you up. So we take 1/2 times negative 1/2 is negative 1/4, minus 1/2 times positive 1/2. And so that's 1/4 minus 1/4 is negative 1/2. So the Jacobian is the absolute value of that, which is 1/2. So please don't say this, because that is not equal. Okay? That is not equal. We have to do the absolute value as a separate operation here. So we will stop here and pick up with this example in the next video. Please don't forget to scan and upload your lecture notes before midnight of the date listed in the course calendar. If you have questions, please come to virtual office hours. If you can't make it to virtual office hours before you need help, please email me, but I need two things. Email me a picture of the problems, because I may not have it handy, and then a picture of your work so I can see how you're approaching the problem. Then I'll be able to help you quickly and efficiently by email. Please take care of yourself and stay safe. We hope to see you next time.